Welcome back to The Deep Dive, the show where we take the source material you've given us, really tear it apart, and piece together the most critical insights.
Yep. Our mission is to give you that shortcut to being genuinely well-informed. We want you to understand not just what the tech does, but the architectural why behind it.
And today's mission is a big one. We're doing a deep exploration of Google Kubernetes Engine, GKE. Now, we know a lot of you listening have probably gotten your feet wet.
Oh, for sure. You've launched an app, you know what a service is, a deployment, the basics. But now you're at that point where you're ready for, let's say, the finer points.
Exactly. This deep dive is built for that intermediate stage. We're moving past just using Kubernetes and into the really critical stuff, configuration decisions, optimization, and all those subtle GKE features that make the difference between a cluster that just works and a system that's truly production grade.
Right. Our goal here is to arm you with that conceptual clarity you'll need to, ace those intermediate challenges and really build a solid foundation for more expert level work down the line.
We have a ton of material to get through, essentially use cases, management modes, some pretty advanced architectural practices. We're going to use all of it as our roadmap.
And we'll make sure we get a balanced look at everything from, say, networking constraints all the way to resilience testing.
Okay, let's unpack this. We're going to start with the most foundational decision you can make. When is GKE even the right choice? And which mode should you use? So let's jump straight into part one. GKE fundamentals and operational modes.
Choosing your platform. Let's do it.
So let's kick things off with a classic scenario from our sources. It's a critical migration decision. You have an application, it's running fine on a serverless platform, something like Cloud Run or Cloud Functions.
Yeah.
But
there's always a but.
Right.
Yeah.
The business is getting complaints from its premium users. And the issue is something called cold start latency.
Yes. This is the textbook signal that you've sort of outgrown the pure serverless model. The absolute genius of serverless is that it scales to zero. No traffic, you pay nothing. The flip side of that coin, though, is the cold start.
Can you just break that down for us? I think a lot of people have heard the term, but maybe haven't really felt the pain of it.
Sure. So when it scales to zero, I mean literally zero, the resources, the container, the whole application environment are completely spun down, gone.
Okay.
So when a request finally comes in, the system has to wake everything up. It has to boot the container, pull the image down, initialize the runtime, Python, Java, whatever it is, and then it can finally serve that request.
And all those steps add up.
They add up to precious seconds of delay. And, for a background job, who cares? But the sources are clear. For premium users who expect an instant response, a few seconds is an eternity. It's unacceptable. You need an instantly available application.
The goal shifts. It's not about minimizing cost anymore. It's about minimizing latency. Where do the guides point us?
Well, there are two paths, and both of them are about keeping the infrastructure warm. You could technically stay on Cloud Run, but you'd have to configure min instances.
And that just tells the platform to keep a certain number of containers running all the time.
Exactly. It forces them to stay ready. But the sources also frame GKE as let's say, the stronger choice here, especially when cost isn't the primary driver.
Okay, so why make that big operational leap to GKE? Why not just set min instances and call it a day?
Granular control. That's the answer. Cloud Run abstracts away a lot of the details, which is great for simplicity. But for high-performance applications, you often need direct control over things like networking protocols.
Like what, for example?
Things like gRPC for really efficient communication between your services, or WebSockets for keeping a connection open. GKE gives you that direct, explicit control over the networking stack. Plus, and this is a big one, it guarantees consistent CPU availability. The trade-off in operational complexity is worth it for that guaranteed low latency performance.
So the minute you need to start tweaking things at the kernel level or the network card, that's when you graduate to GKE.
That's a perfect way to put it.
Makes total sense.
Okay.
Okay, so we've decided GKE is the answer. Now we hit this huge fork in the road, standard versus autopilot.
And this is where Google Cloud is directly tackling the biggest historical headache of adopting Kubernetes, all that management overhead.
Right. Kubernetes is powerful because it's open source, it's portable.
But managing the actual worker nodes, that's where the complexity really bites you. You're patching the OS, worrying about security, capacity planning, and you're constantly playing this a complex game of Tetris called bin packing.
Okay, let's pause on bin packing. That's a classic bit of jargon. I think an analogy would really help here.
Definitely. Imagine you're trying to fit a bunch of different sized boxes, those are your pods, into a limited number of delivery trucks, which are your nodes.
Right.
If you only have small trucks, you can't fit your big memory-hungry box, even if the truck's engine, the CPU is powerful enough. So you have to decide what size trucks to order, and you're constantly trying to make sure they're not driving around half empty. That whole mental effort of optimizing the truck space, that's bin packing.
And if you get it wrong, you're either wasting money on empty space in the truck or you just run out of room entirely.
Exactly. It's tedious.
So autopilot is basically the easy button that gets rid of all of that.
Precisely. Autopilot's philosophy is, just tell me what your application needs, and I'll figure out the trucks. You, the user, you completely stop worrying about what VM type to use, or if the OS needs patching. Autopilot just handles it. It's for people who want the power of Kubernetes without needing to become full-time infrastructure engineers.
And the sources emphasize that this is backed by a really different billing model. It's pay for what you request at the pod level. That seems like a huge shift.
It's a massive shift. With GKE standard, you're essentially renting the whole truck. You get a 16-core VM, you pay for all 16 cores, even if your boxes only take up half the space.
That's wasted money.
A lot of it. With Autopilot, the bill shifts to the resources your pods actually request. You ask for 2 CPUs and 4 GB of RAM for a pod. You pay for those 2 CPUs and 4 GB of RAM. You're no longer paying for the empty space in the truck, just the boxes themselves.
So standard is for when you need maximum control, maybe special GPUs or a custom kernel, but you take on all the management. Autopilot is for simplicity and optimized billing, and you give up control over the node details.
That's the trade-off in a nutshell. Maximum control versus maximum operational simplicity.
All right, we've picked our mode. Now, let's talk about the actual first steps to get something running. It seems really fundamental to separate the jobs of the two main command line tools, GI Cloud and kubectl.
It is, and it trips up a lot of beginners. The key thing to realize is you can't deploy an application into a Kubernetes cluster until the cluster itself actually exists. The tools just reflect that two-step process.
So step one is creating the cluster, building the infrastructure.
Correct. And for that, you have to use GCloud, the Google Cloud CLI. GCloud is the tool that talks to all of Google Cloud. When you run Cloud Container Clusters Create, you're provisioning the actual physical, virtual resources. The VMs for the nodes, the networking, the control plane.
You're building the engine room?
Great analogy. You're building the engine room, and once it's built and running, then you move to step 2.
Resource deployment. And that's when we switch tools.
Right. You switch over to kubectl. Kubectl is the native Kubernetes tool. It knows nothing about Google Cloud's billing or its specific VMs. It only knows how to talk to the Kubernetes API server inside the cluster that GKE just built.
So its job is to manage the application inside the cluster.
Exactly. Deployments, services, config maps, all the Kubernetes objects. GKE builds the cluster. Kubectl manages the workloads within it.
The analogy holds up. GKE builds the engine room and wires it up, and kubectl drives the ship, managing the cargo and crew. That distinction feels essential to really mastering GKE.
It really is. It defines the boundary between cloud infrastructure and container orchestration.
All right, let's shift gears. In part 2, let's get into performance. A common struggle for developers is slow deployment times. Our sources have a scenario where a developer is seeing long builds specifically because of how their Dockerfile is structured.
Oh yeah, this is one of those simple fixes that can have a massive impact. The problem almost always comes down to 2 things: image size and how well you're using the cache.
Okay, let's break down the 2 optimizations from the materials. First up, choosing a slimmed-down base image, something like Alpine Linux. Why does that matter so much for speed?
Every container image is built in layers. The base image is the first and usually the biggest layer. If you use something like a full Ubuntu image, that layer can be hundreds of megabytes full of tools and libraries your app will never, ever touch.
And you pay a penalty for that size every time you deploy.
You do. That huge layer has to be sent over the network from your container registry down to the GKE node. Alpine Linux, on the other hand, is tiny. It's built for efficiency. Using it can slash your image size and dramatically cut down that network transfer time. It's like rule number 1.
Okay, so that's the image size. The second optimization is about the build time itself, and this is where layer caching comes in. The recommendation is to copy your source code after you install all your heavy dependencies.
So wait, you're saying the order of the commands in the Dockerfile matters that much?
It's everything. A Docker build works step by step, layer by layer. If any line in your Dockerfile changes, Docker throws away the cache for that layer and every single layer after it.
Okay.
Now think about it. Installing your dependencies, like using pip for Python, that's slow, but those dependencies don't change very often. Your application source code, however, changes all the time, multiple times a day.
Ah, I see where this is going. If I copy my source code at the beginning of the file.
Then every single time you fix a typo, you invalidate the cache and Docker has to reinstall all of your heavy dependencies from scratch. It's a massive waste of time.
But if I install the stable heavy dependencies first, and then copy my changing source code last, you've just stabilized the most expensive part of your build. Docker sees the dependency layer hasn't changed, uses the cache instantly, and only has to rebuild that tiny final layer with your code change. You save a huge amount of time. It's a simple architectural pattern that makes a world of difference.
That is a brilliant distinction. It's not just about building, it's about structuring the build for efficiency. Okay, so we've got our optimized containers running. Now let's talk reliability. We have an application, echo deployment, and we need to update it with zero downtime.
The great thing about Kubernetes is that this is a solved problem. The default strategy is called a rolling update, and the simplest, safest way to trigger it is with the command kubectl set image techo deployment new image.
Now, why not just delete the old deployment and create a new one? That seems like it would be faster, maybe.
That's a great question, and it gets at a common mistake. Deleting and recreating is what's called a destructive update. You are creating a very real window of time where the application just doesn't exist. The service has no healthy pods to send traffic to.
So user requests will fail.
They absolutely will. You're basically engineering a small outage. A rolling update, on the other hand, avoids this completely.
How does it do that?
The kubectl set image command tells the control plane to be graceful. It starts by bringing up the new pods with the new image, and importantly, it waits for those new pods to pass their health checks before it even thinks about taking the old ones down.
And that's the key, right? It's that overlap.
The overlap, exactly. So there's never a moment of total downtime. The service always has healthy pods available to serve traffic, seamlessly managing the transition from the old version to the new one.
That's perfect for stateless applications, where any pod can be replaced by another. But what happens when our application is stateful? You know, something that needs a persistent, unique identity, like a database.
Ah, now we're moving into the really interesting stuff, distributed systems. A standard deployment treats all its pods as completely interchangeable cattle. A pod crashes, Kubernetes replaces it with a new one that has a totally random host name. For a web server, that's fine.
But for a database cluster, that would be chaos.
Complete chaos. Databases, message queues, they rely on having a consistent set of host names. They need to know that they are database 0, database 1, and database 2, and that that identity is stable.
And a regular deployment can't provide that.
It can't. For that, you need a specialized Kubernetes resource called a stateful set. A stateful set is designed specifically to manage a group of pods that need to maintain those sticky identities.
So if database 1 crashes, when the new pod comes up, it actually becomes database 1 again. Same name, same network identity.
That is its crucial feature. It ensures stable, unique network identifiers, even across restarts. And it does more. It provides ordering guarantees, making sure database 0 starts before database 1, for example. This is critical for systems that need to establish a quorum or replicate data in a specific sequence.
So while a persistent volume gives you the stable storage, the stateful set gives you the stable identity and ordering.
You've got it. It's a critical architectural distinction. Deployments for interchangeability, stateful sets for stable identity.
This brings us to part 3, which is really the heart of intermediate GKE scaling. Not just adding more machines by hand, but building a system that automatically adapts to load.
And this is all about the relationship between two separate but deeply connected components. If you only use one, you're going to hit a wall or waste a lot of money.
Okay, let's spend some time on these 2 pillars of GKE autoscaling. Pillar 1 is about scaling the application itself, the number of containers.
That's the horizontal pod autoscaler, or HPA. The HPA lives inside the Kubernetes control plane. It just sits there and watches a metric, usually CPU utilization.
Okay.
You tell it, I want my pods to run at about 50% CPU. If the load increases and they hit 80%, the HPA wakes up and says, whoa, we need more hands on deck, and it creates new pod replicas to spread the load out.
Got it. It manages the supply of application instances. So what's pillar 2?
Pillar 2 is scaling the infrastructure, the actual machines. That's the cluster autoscaler, or CA. The CA lives at the Google Cloud infrastructure level outside of Kubernetes.
So what does it do?
It watches the overall health of the cluster. So when your HPA decides to scale up the pods, those new pods need somewhere to run. They need a node with available space.
And if all the existing nodes are full,
Those pods get stuck in a pending state. They're waiting for a home. The cluster autoscaler sees these pending pods and says, we're out of room, and it automatically provisions a new node, a new compute engine VM for them to run on.
so HPA is like the manager saying, we need more cashiers, and the CA is the HR department actually hiring them and giving them a register to work at. You absolutely need both.
It's the perfect analogy. If you only have HPA, you'll ask for more cashiers until every register is full, and then new customers just have to wait in line. If you only have CA, you might hire a bunch of people, but they just stand around doing nothing because no one told them to open a new lane.
The synergy is everything.
Yeah.
HPA creates the demand signal, and CA provides the capacity to meet it.
That's it.
And for anyone who set up a cluster without this and now needs it, the materials show how to enable it on an existing cluster.
Yeah, and since it's an infrastructure change, you use JAG Cloud. The command is JAG Cloud Alpha Container Clusters update my cluster, enable auto-scaling, and then you set your min nodes and max nodes. Using the update command is key, and you have to define those boundaries so you don't accidentally scale to 1,000 nodes and get a surprise bill.
A very important detail. Okay, let's go beyond a CPU. The sources have this great intermediate scenario. An IO-intensive app pulls from PubSub, writes to a database is falling behind, messages are piling up, but when you look at the cluster, CPU usage is low.
This is a classic trap. The CPU is low because the application isn't busy calculating anything. It's busy waiting. Waiting for the network, waiting for the disk write to finish.
So the CPU metric is giving you a false positive. It's saying everything's fine, but meanwhile the business is on fire because work isn't getting done.
Exactly. The real indicator of the workload isn't an internal metric at all. It's an external one. It's the size of that PubSub queue. The number of undelivered messages is the true demand signal.
So how do you get Kubernetes to watch a PubSub queue?
This is where the tight integration with Google Cloud Monitoring comes in. You can configure the HPA to scale not on CPU, but on an external metric from Cloud Monitoring. In this case, it's subscription and delivered messages.
Wow.
You basically tell the HPA, hey, if the number of messages in this queue goes above 100, start adding more pods until it comes back down. This ties your scaling directly to the actual work that needs to be done. It's a huge step up in sophistication.
That is a real aha moment. You're scaling based on the task, not just the temperature of the machine.
Precisely.
Okay, last one for this section. Cost reduction. We have a huge 200-node GKE cluster. It's running everything. Batch jobs, stateful apps, stateless web servers. The goal is to slash costs, but keep everything available.
You have to be careful here. You can't just use a blunt instrument like throwing preemptible VMs at everything because that'll kill your stateful apps. The key is precision.
So what's the recommended strategy?
It's a two-layer approach that combines what we've just talked about. First, you configure HPA on everything you possibly can, all your stateless and stateful apps that can scale. This forces the pods to be right-sized, scaling down when they're idle.
Okay, so you're tightening up the demand side.
Exactly. Then you enable the cluster autoscaler. Because the HPA is now aggressively scaling pods down, the CA will see nodes become underutilized or completely empty.
And it will just get rid of them.
It will safely drain the remaining pods off and terminate the node. The two work together in a virtuous cycle. You stop paying for nodes that are only 30% utilized. HPA ensures every active node is packed efficiently, and CA gets rid of any nodes that become slack. It's how you eliminate waste.
Okay, part 4. Let's get into networking and traffic management. We've got our apps running and scaling, but now we need to make sure they can talk to each other and the outside world securely and efficiently.
Let's start with the basics, internal communication. You have a back-end microservice with, say, 3 replicas, and a front-end needs to talk to it. How does the front-end find it when the pod IPs are always changing?
Right, you need some kind of stable address.
And that stable address is provided by the Kubernetes service resource. The default type, cluster IP, is made for this. You create a service that points to your back-end deployment. That service gets a stable, internal-only IP address, and more importantly, a stable DNS name, something like backend-api.default.sbc.cluster.local.
And the front end just uses that DNS name forever.
Forever. The service acts as a simple load balancer, automatically distributing traffic to whichever of the back-end pods are currently healthy and running. The pods can come and go, but that service name never changes.
Quick distinction here. Why a service and not an ingress for this?
Good question. Ingress is really for traffic coming from outside the cluster, usually HTTP or HTTPS. It's about routing external requests based on a host name or a URL path. For internal service-to-service communication, cluster IT services are the dedicated, more secure tool for the job.
Okay, let's throw a wrench in the works. We're migrating a legacy app, and it's hard-coded to talk to a specific static internal IP address. It can't use DNS.
Ah, the legacy constraint. This means we have to bridge the Kubernetes world with the underlying Google Cloud Network. We need to provision a proper internal load balancer with a static IP that we choose.
And how do you request that from inside Kubernetes?
We still use a service, but we change its type to load balancer. And then we add a specific annotation to the manifest. Annotations are just little key value pairs that act as instructions for the cloud provider. In this case, we add an annotation that tells GKE, hey, I need an internal load balancer, and please assign it this specific static IP address.
So the service resource is way more versatile than it looks. It can be a simple internal DNS entry, or it can be this sophisticated remote control for provisioning complex cloud load balancers.
That's a great way to think about it. It's the declarative bridge between the portable Kubernetes API and the specific features of Google Cloud.
Moving up to a global scale. Our API is expanding from the US to Asia. We need to cut down latency for those Asian customers and have multi-region availability. The goal is a single global IP that routes users to the closest cluster.
For that kind of true global routing, you need a global HTTPS load balancer. The tool the sources point to for this is Kubemshi, which stands for Kubernetes Multi-Cluster Ingress.
So what's the process?
First, you set up a second GKE cluster in, say, Asia Southeast 1 and deploy your app there. Then you use the Kubemshi tool. It automatically provisions a single global Google Cloud HTTPS load balancer that knows about both of your GKE clusters. This load balancer gets a single global Anycast IP address.
Let's explain Anycast IP. Why is that the magic ingredient?
Anycast is a networking technique where the same IP address is advertised from multiple places in the world at the same time. When a user in Singapore tries to connect to that IP, their traffic is automatically routed to the closest network edge, which in this case would be your Asia Southeast 1 cluster. A user in Ohio connects to the same IP and gets routed to your Central 1 cluster.
So Kubemshi builds this amazing abstraction where two separate clusters in different continents act like one single globally aware application. The regional boundaries just disappear for the user.
It's an incredibly powerful way to handle disaster recovery, global load balancing, and latency optimization all at once.
Okay, final networking challenge, and this one is expert level. A company has a strict security policy. No GKE worker nodes are allowed to have public IP addresses, period. But the application on those nodes needs to call out to third-party APIs on the public internet.
This is a classic security versus functionality puzzle. You have to lock down the nodes, but still give them a way to talk to the outside world.
And there's a two-part solution for this, right?
Yes, you need both pieces.
Mm-hmm.
Step 1. You configure your GKE cluster as a private cluster. This is a setting that tells GKE to only give the nodes internal private IP addresses. That satisfies the policy.
Okay, but now those nodes are trapped. They can't initiate a connection to the public internet.
And that brings us to step 2. You have to configure a Cloud NAT gateway for the subnet that the cluster lives in. The NAT gateway acts as a secure proxy. The private nodes send their outbound traffic to the NAT gateway, which then translates their private IP into one of its public IPs, sends the request out to the internet, and manages the response back.
So the nodes themselves never have a public identity, but they can still reach out through this managed secure gateway.
Exactly. It gives you the outbound connectivity you need without violating the core security policy. It's a perfect example of how an advanced GKE solution often involves orchestrating multiple Google Cloud services together.
All right, part 5. We've built our infrastructure, we've wired it up. Now we get into the day-to-day operational stuff. Observability, security, and making sure this whole thing is resilient.
And let's start with a crisis. All the pods for your app are crashing every 2 seconds. It's a classic crash loop. You know the application logs its errors to standard output.
But the pods are restarting so fast, you can't possibly queue back logs into one before it disappears. You need a centralized place to look.
You do. And GKE's integration with Google Cloud Operations, what used to be called Stackdriver, is built for this. By default, everything written to standard output and standard error in your containers gets automatically forwarded to the centralized logging system. So the right move, the only move really, is to go look at the Stackdriver logs for that container. The fatal error will be right there.
And what if someone somehow turned logging off? What's the fallback?
In that case, the quickest fix with the least disruption is to just update the existing cluster and enable cloud operations for GKE. It's a simple config change. As soon as you flip that switch, the logs and metrics will start flowing, and you can use the GKE monitoring dashboard to figure out what's going on.
That flows right into our next topic, SRE triage. An incident is happening. What's the fastest way to figure out the system's health?
You always start with the path of least resistance. GKE gives you so many great metrics out of the box, so the sources are really clear on this. Start with the predefined dashboards in cloud monitoring.
These are the dashboards that Google's own engineers built, right? They're designed to show the most critical indicators for a GKE cluster.
Exactly. Control plane health, API server latency, node utilization. It's all there. It's your fastest path to see if there's a systemic platform-level problem. Only after you've checked those and ruled out the obvious should you start diving into custom queries and building your own charts.
Let's switch from reactive to proactive.
Yeah.
We're seeing outages during deployments because a bad configuration only shows up in production. We need some kind of internal health check.
And this is where you absolutely must configure liveness and readiness probes in your pod spec. This is non-negotiable for any serious GKE workload.
Okay, let's be really clear on the difference because they're easy to confuse. What does a liveness probe do and what happens when it fails?
A liveness probe is the container's heartbeat. It answers the question, is the application inside this container still running and healthy? If that probe fails, maybe the app is deadlocked. Kubernetes assumes the container is broken, and its only corrective action is to kill it and start a new one. It's for self-healing.
Got it. So what of the readiness probe? How does that prevent deployment outages?
The readiness probe is the open for business sign. It answers a different question. Is this container ready to accept traffic? An app might be alive, but it could still be starting up, loading data, connecting to a database.
So it's not ready yet.
Right. And if the readiness probe fails, Kubernetes does something different. It doesn't kill the pod. Instead, the service that sits in front of the pod stops sending it traffic. This is critical for rolling updates. It guarantees that a new pod is 100% ready to go before a single user request ever hits it.
Liveness is for survival. Readiness is for traffic management.
Perfect summary.
Okay, shifting to pipeline security. The problem. Developers can accidentally or intentionally deploy something to production without it passing all the tests in dev and staging. We need to enforce the process.
You need a digital gatekeeper on the cluster itself. And the solution here is a combination of binary authorization and attestations.
How does that work?
You enable a binary authorization policy on your production GKE cluster. That policy is a simple rule. Do not run any container image unless it has a valid digital signature from an approved source.
And where does that signature come from?
It comes from your CI/CD pipeline, like Cloud Build. As your image passes your unit tests, your integration tests, and staging. At the end of that successful stage, the pipeline generates an attestation. That's the cryptographic signature, the stamp of approval.
So if someone tries to deploy an image directly to production that skipped the staging tests,
the binary authorization policy on the cluster will check for that staging attestation, it won't find it, and it will block the deployment cold. It's how you enforce that your tested code is the only code that runs in production.
that's a powerful control. Now for some really advanced testing, chaos engineering. We want to see what happens when a specific microservice starts failing. But we want to do it surgically, without actually destroying anything.
For that kind of precise application-level failure testing, you need a service mesh. And the tool for the job is Istio, specifically its fault injection feature.
So Istio manages all the traffic between services. How does that help us break things in a controlled way?
Because Istio sits in the middle of every request, it can manipulate them. You can write a rule that says, for the next 5 minutes, for any request going to the checkout service, don't actually send it. Instead, just return an HTTP 500 error. Or you could say, add a 2-second delay to every response.
So you can perfectly simulate a failing or slow dependency without touching a single pod or node.
Exactly. It lets you test your application's resilience, its timeouts, its retries, its circuit breakers, in a completely controlled and repeatable way.
Last one, the big legacy problem. There's a critical app on an old Linux VM. We need to move it to GKE, but the source code is long gone. We can't rebuild it as a container.
This is where you need a tool that can containerize the entire environment, not just the app. And for that, there's Migrate to Containers, which is part of the Anthos suite.
And what does it do? Is it like magic?
It's pretty close. It's an automated tool that connects to the running VM, analyzes its entire file system, the running processes, all the dependencies, and it packages that entire state up into a production-ready Docker image.
So it performs a lift and shift directly into a container that can run on GKE.
That's exactly what it does. It bridges that gap, allowing you to modernize the platform for a legacy application, even when you can't modernize the application itself. It's a huge enabler for cloud adoption.
What a deep dive. We really went far beyond the basics there and focused on the why behind all these decisions.
We really did. We covered things like optimizing your Dockerfile for layer caching, ensuring zero downtime updates with the rolling update strategy.
And we really dissected that synergy between the horizontal pod autoscaler and the cluster autoscaler. I think that insight about scaling I/O apps based on an external metric like a pub sub queue is a real game changer for people.
Absolutely. And we hit on some sophisticated networking too, from using annotations to get a static internal IP all the way to that expert level pattern of using a private cluster with CloudNAT for security.
Plus, the production guardrails. Knowing the difference between liveness and readiness probes and using binary authorization to lock down your deployment pipeline.
I think if you followed along with all this, you're not just a GKE user anymore. You have the architectural foundation to be a GKE architect. This should give you the confidence to tackle some really advanced challenges.
For sure. And let's leave you with a final thought to chew on. We talked about Kubemshi, how it can make two GKE clusters on opposite sides of the planet act as one single unit behind a global IP. Now, if our tools can completely abstract away geography like that, making regional boundaries almost meaningless for performance and availability, what does that level of abstraction mean for how we even define infrastructure in the future?
Something to think about. Thanks for joining us for the deep dive. We'll see you next time.